The second semester of calculus is dominated by this idea of trying to find the area under a curve. And when you calculate an integral, that's exactly what you're doing. But the integral is actually based on a concept called a Riemann sum, which is a way of approximating the area under a curve using rectangles and in some cases trapezoids. In this video, I'm going to demonstrate for you the four most common methods of calculating a Riemann sum. Let's start with Lram. This is the left rectangle approximation method. The directions tell us to approximate the area under this curve from x equals 0 to x equals 10 using 5 subintervals of equal width. So if we take the number line from 0 to 10 and we divide it evenly 5 times, then the intervals will be from here to here, from here to here, here to here, here to here, and from here to here. So obviously the width of each one of these intervals is 2 in every case. So the left rectangle approximation method means that we are supposed to draw rectangles that have the width of each interval, but the left side of the rectangle touches the curve. So the left side of each rectangle, the height is going to be the value of the function at that corner. So there's my first rectangle, and for the second interval, I'm drawing my rectangle and I'm going to keep going up and up until the left edge of the rectangle meets the curve. So my third rectangle is going to look like this, and it's going to go up to here because this is where it meets the function. Now the next one is sort of interesting because if I try to draw any rectangle at all, I am immediately above where the function is if I'm looking at the left edge over here. So this will actually be a degenerate rectangle, which is nothing at all. But my final rectangle, again, there's my width, and I'm going to go up and make the rectangle taller until the left edge touches the function. So I'm going to use these rectangles to approximate the area under the curve. You know that the area of a rectangle is base times height. So we're just going to approximate the area by doing base times height over and over again and adding. So for the first rectangle, the area, base times height, is going to be 2 times 3. And then for my second rectangle, base times height is going to be 2 times 6. And then third rectangle, base times height is 2 times 3. For the fourth rectangle, so-called rectangle, I really wouldn't have to write anything, but since we are practicing for the AP exam, I would recommend to go ahead and put an expression even representing this flat non-rectangle. So the base times height of this nothing rectangle is going to be 2 times 0. That's just so the whoever's grading your AP exam can follow your thought process, and they can see what you were doing for that rectangle. And then the final rectangle, base times height is 2 times 3. So this is an expression for the approximate area under this curve using these 5 rectangles. And really, you're going to want to just go ahead and leave it like this. Of course, you could go ahead and calculate this out and come up with a single number. But on the AP exam, they will accept an expression just like this and give you full credit. So there's no need to waste time working this out to an actual single number answer. The second method is almost the same. This is RRAM, right rectangle approximation method, And you can probably guess what I'm going to do. So I'm still making rectangles, but because it is the right rectangle approximation, this time I'm focusing on the right edge of the rectangle, and it is the right side of the rectangle that will touch the function. Okay, so there's my first rectangle and my second rectangle. I bring it up until the right edge touches the function. And for this problem, it's the third rectangle that has this weird case of you can't make a rectangle at all because it's immediately above the function. So this is going to be my strange non-rectangle, my zero rectangle. But then my fourth rectangle is okay. It's going to have a height of 3 as it touches the function, and my final rectangle is also going to have a height of 3. So here comes my expression for the approximation of the area under this curve by adding the area of each of these 5 rectangles. So base times height again. So the first one is going to be 2 times 6. And then my second rectangle, base times height, is 2 times 3. And then here comes my strange 0 rectangle, so I'll just put that in as 2 times 0. My fourth rectangle, base times height, is 2 times 3. And then the last rectangle, again, base times height is 2 times 3. And you can feel free to go ahead and calculate this out and get a single number if you want to, but I'm going to leave it like this, and the AP graders would give you full credit for this answer. The third method is called Mram, Midpoint Rectangle Approximation Method. So for this method, we are going to find the value of the function at the midpoint of each interval, and that is going to give us the height of each rectangle. So here's the midpoint of the first interval, and here's the value of the function. Here's the midpoint of the second interval, and here is the value of the function. All right, third interval, midpoint, and so I have to estimate a little bit here, but it seems like the value of the function is about here. Here's the midpoint of the fourth interval, and the value of the function is about here. And here's the midpoint of the fifth interval, and the value of the function is about here. So I'm going to draw my rectangles like I did for the previous problems, but now the height of each rectangle is going to be the value of the function at those midpoints. So here will be the height of my first rectangle, and here comes the height of my second rectangle. And my third little baby rectangle comes up to here. My fourth one is doing the same type of thing. Those will be at the same height. And my fifth rectangle. All right, it's all about the midpoints, the value of the function at each midpoint. So we were warned that we were going to have to do some approximation of these y values. So we will just do our best. So the first rectangle, remember for each of these areas, we're just doing base times height, since that's how you find the area of a rectangle. So all of the bases are 2 as before. The height of this first rectangle is clearly 5, so that part is super easy. So we will do 2 times 5. And then the second rectangle, base times height, is 2 times 5 again. All right, and then here's where I get a little uncomfortable because I really hate estimating like this, but this height seems to be maybe 0.7-ish. So I'm going to say 2 times 0.7. And then the second one, well, this is the fourth rectangle, will be the same. Base times height is 2 times 0.7 again. And then the last one, let's see, well, the height This seems to be about maybe 4.3, 4.2. I'm going to call it 4.2. So let's see. So I'll go 2 times 4.2. So this is going to be a pretty decent approximation for the area under the curve using these 5 rectangles. That's how you do Mram. Let's move on to the fourth method, which is called TSAM for Trapezoidal Sum Approximation method. So we're going to be using trapezoids to estimate the area under the curve instead of adding up a bunch of rectangles. So let's review what we know about trapezoids. So a trapezoid is going to have 2 parallel sides. Each of them is called a base. So we could say this is base 1 and this is base 2. A trapezoid has a height, and that's going to be the distance between the 2 bases. So this distance right here would be considered the height of the trapezoid. Based on these values, we would say that the area of the trapezoid is 1/2 the sum of the bases times the height. Of course, you can easily imagine making one of the sides of this trapezoid vertical. That doesn't change anything. We still have a trapezoid, 2 bases, and a height. But now I want you to imagine rotating this trapezoid in this direction. So we're going to stand it up on its end. Oriented this way, we see that the bases of the trapezoid are now these vertical lines. So we have base 1, say, over here, and base 2 is going to be here. Now, oriented this way, what we were previously calling the height of the trapezoid is now more of a width of the trapezoid. So this is the height that we were referring to when we said 1/2 base 1 plus base 2 times height, but we will probably be more comfortable referring to this as a width now. So if I write the formula this way, it'll be 1/2 base 1 plus base 2 times that width. So we can use trapezoids oriented this way to approximate the area under this curve. We will do that by using vertical lines which rise to exactly the height of the function on either side of the interval. And then if we connect the ends of those vertical lines, we will have our trapezoid. So let's go ahead and write an expression for the area of this trapezoid. Remember, the area will be 1/2 base 1 plus base 2 times the width of the trapezoid. So here we go. Area of this first little trapezoid is 1/2. Remember, base 1 will be the first vertical line. So base 1 has a length of 3. Plus base 2, which is the second vertical line, which has a length of 6. And then times the width of the trapezoid. Well, the width of each trapezoid is going to end up being 2. So here's an expression for the area of the first trapezoid. Of course, we will end up with 5 of these expressions to approximate the area under the curve. Let's go ahead and draw the second trapezoid now. So for the second trapezoid, we can still use the first vertical line that we have. We'll just add in another vertical line on the other side of the interval, and we'll connect the ends, and there is our trapezoid. So adding on the area of the second trapezoid. So here we go, 1/2 base 1 plus base 2. Base 1 is 6, base 2 is 3. So we will say 6 plus 3. And then times the width, which will always be 2. So there's the second trapezoid. Our third trapezoid will be a degenerate non-trapezoid. And you'll see what I mean. Whoops. Because on the right-hand side of this interval, the function is at 0. So there is no vertical line that I can actually draw. So instead, this is going to wind up really being a triangle. But let's just stick to the same pattern. So if we use our imaginations, we can sort of pretend that this is a trapezoid where base 1 is 3 and base 2 is simply 0. So in that way, we can just stick to the same pattern. So 1/2 base 1 plus base 2. So that's 3 plus 0. And then times the width, which again is 2. It'll be the same situation for the next little trapezoid, non-trapezoid, because we're still here at 0. We can't make a vertical line there. So instead, we will end up making this triangle. So same deal. We will look at this as base 1 and base 2, where base 1 just happens to be 0, while base 2 is 3. So here we go. That's going to be plus 1/2 base 1 of 0 plus base 2 of 3, and then times that width. So now we can draw our final trapezoid. So let's put our vertical line on the right-hand side of the interval. So this, really is not technically a trapezoid either. You can see that it's actually forming a rectangle. But again, let's just use our imaginations and sort of pretend this is a trapezoid, where base 1 is 3 and base 2 is 3. So if we scroll over here and add this on the end, we will have plus 1/2 base 1 plus base 2 times that width. I think back here I accidentally put a width of 3 when that was supposed to be that width of 2 that we always have. So really, this long expression that we have right now is an expression for the approximate area under this curve. So you could leave this entire thing just like this for your answer, and that would be perfectly acceptable for the AP exam. What a lot of people will do is they will go ahead and calculate this part of each expression, which is pretty easy to do. So your teacher might prefer for you to go ahead and simplify this part of each expression. If we go ahead and do that, so 3 plus 6, that's going to be 9. So this is going to be 9 over 2. So we have 9 over 2 times 2. And then we can just do that for each expression. So here, for the next one, we have another 9 over 2 times that width of 2. For the third one, 3 plus 0 is 3, so we have 3 over 2 times 2. And it's the same situation for the next one. So here comes another 3 over 2 times 2. And then the last one over here, 3 plus 3 is 6. And then 6 divided by 2 is 3. So we can just go ahead and put 3 times 2. So a lot of people will go ahead and put this for their approximation for the area under the curve using the TSAM method, trapezoidal sum approximation. So here's one more thing I want to add on to this video. In each of these methods, we are either going to end up with an overestimate or an underestimate of the actual area under the curve. So let's consider each method and decide whether we're going to have an estimate that's a little bit bigger than it should be, an overestimate, or whether we will have an underestimate, which will be an estimate that's a little bit less than the actual area under the curve. Let's start with LRAM, the left rectangle approximation. I think we can get away with drawing a single rectangle to give us the idea. Let's just pick an interval, let's say from here to here. If we want to do the left rectangle approximation method, then we will draw our rectangle in such a way that the left edge of the rectangle just touches the function. So notice that in this case, we've got this extra space above the rectangle that's being left out. We are trying to use this rectangle to approximate this portion of the area under this curve. But the rectangle area is less than the actual area under the curve in this interval. So we have an underestimate. A big part of the AP exam is justifying your answer. It turns out that the LRAM method is always going to give us an underestimate when the function is increasing along that interval. So our justification will be because function f is increasing. When you justify your answers, always be very specific. Always avoid using phrases like the function, too vague. So they specifically called this function f. So in my justification, they specifically call this function f. So in my justification, I say because f is increasing. So always avoid vague use of the expression the function. You are allowed to abbreviate this, by the way, so a lot of times instead of writing out the whole word increasing, I will just put INC for increasing. So it'll be very similar for the RRAM method. So for RRAM, we're talking right rectangle approximation. So we will draw our rectangle, but we will focus our eyes on the right side of the rectangle, and we will draw it so that the height of the rectangle on the right hand side is right at the value of the function. So in this case, notice how the rectangle has this extra area to it that goes above and beyond the area of the actual curve in this interval. So this is going to be an overestimate. The right rectangle approximation method will always give you an overestimate when the function is increasing. So just like before, our justification will be because f is increasing. Just for comparison, let's look at what would happen if we had a decreasing function like this one. If we did the left rectangle approximation, all right, here's the left side of my rectangle touching the function. Notice that now we're getting an overestimate. So it's just the opposite. What if we do the RRAM, the right rectangle approximation? So focus on the right-hand side of this rectangle, and there it's just barely touching. But notice this time the area is too small. We've got this extra space above the rectangle that's being left out and ignored. So now suddenly we have an underestimate instead of an overestimate. So I would recommend you don't necessarily need to memorize this. You can easily just draw a quick picture and remind yourself. The important thing is that you understand that it's all about whether or not the function is increasing when you're talking about rectangles. Finally, what about the trapezoidal sum approximation method? So let's draw one trapezoid, which would be something like this. All right, we have our two vertical bases, and then we connect the ends to form our trapezoid. So one of the reasons why the trapezoidal method is sometimes preferred, even though it's a little bit more complicated to calculate, is because it is a better approximation. So this is going to be an underestimate, because you can see that we do have a little bit of this area that's being left out of the trapezoid. So this is an underestimate, but it is a better approximation than either of the rectangle methods. So here's the part that you need to memorize. When it came to either of the rectangle approximation methods, when you wanted to decide if you have an overestimate or an underestimate, you had to look at whether or not the function is increasing or decreasing. When you are dealing with the other two approximation methods, TSAM or Mram, it's all about the concavity of the function. Is the function concave up, or is the function concave down on this interval? So that's going to give us the reason why the TSAM method is giving us an underestimate. On this interval, function f is concave down. So we will say because f is concave down. Just memorize that Mram works the opposite of TSAM. I could draw you a little picture of it, but it wouldn't really convince you of why Mram is actually going to give you an overestimate. Again, you don't need to memorize all of this. Just memorize that when you're dealing with the rectangle methods, it's all about increasing or decreasing. Is the function increasing or decreasing? If you're dealing with the other two methods, just memorize that those are all about concavity of the function. Now, as far as which will give you overestimate and which will give you an underestimate, you can just draw yourself a quick sketch of a rectangle or a trapezoid and see for yourself if it's an overestimate or not. For Mram, I would just draw a trapezoid, and if a trapezoid gives you an underestimate, then Mram will give you an overestimate. So I've been telling you that when it comes to TSAM and Mram, if you want to decide if you have an underestimate or an overestimate, it's all about the concavity of the function. Is it concave up or concave down? So for this example, we had a function that was concave down, and TSAM gave us an underestimate, and I told you to trust me that Mram would give you then an overestimate. But let's go ahead and look at a quick example of a function that is concave up. So here's function g. Function g is still increasing just like the last example. The only difference is function g is concave up, whereas the function f was concave down. So let's check our trapezoidal sum approximation method by drawing a single trapezoid. I'm going to make a sort of a large interval, maybe from like here to here, just so you can see better what's happening. So here comes our trapezoid. We need vertical lines at the ends of the interval. Those are the bases of our trapezoid. And then we will form the other two sides of the trapezoid by connecting these ends, like this. So here is our trapezoid. So think about it to yourself for a second. Is this trapezoid an underestimate or an overestimate? So hopefully you can see that this is definitely going to be an overestimate because we've captured all of this extra space that is not actually under the curve. So this trapezoid is giving us an overestimate. And for your justification, you would say because g is concave up. And if I were you, I would just memorize that Mram is the opposite. So Mram would then be an underestimate because g is concave up. Notice one more time that this is the opposite of what we got for TSAM and Mram when the function was concave down. So when it's concave up, TSAM is giving us an overestimate, but when the function was concave down, TSAM gave us an underestimate.